Okay, welcome to the 2025 DAFoam workshop. And my name is Ping, and I am the organizer of this workshop. Today I see that right now we have 14 participants, and very glad to see you are here. And I'm seeing that a few more are joining. As you probably remember, I sent you an email yesterday talking about some details about this workshop. This workshop will be about 2 hours, and we will have two sections. And one is focused more on the user, the other focus more on developers. And in between, we may have a 5-minute break. As you can see there, we don't have a Q&A section today, so that's why if you have any questions, please feel free to stop me and ask at any time. Okay. Objectives. I also will ask all the participants, please mute yourself. But if you have any questions, please feel free to ask at any time, or you can send a message in the chat. Okay, so we have 3 objectives. After this lecture, you should be able to first identify some new APIs and run scripts in DAFoam version 4. And this workshop focus mostly on the new version 4 in DAFoam. And the first objective is that you should be able to know what these new APIs are. The second objective is to get familiar with the new code structure and how you can add new features. This is more for developers. And lastly, you should be able to run some tutorials, and I will also show you how to add new features with some hands-on examples. Here's the outline. As I mentioned, we have 2 sections. Part 1 will focus on users. Part 2 will focus on developers. And I want to highlight that we assume that you are already familiar with the version 3 of DAFoam. So that's why. And especially the first part, we will focus mostly on the delta difference, what new features are in DAFoam version 4. Okay, let's go to the first part. User-focused features. And the objective is we changed some APIs in the run script.py to let DAFoam's API be more consistent with the OpenMDAO standard. Okay, I will talk about the details of these new APIs, new interface or new APIs in the run scripts. So first thing I want to highlight that if you are still using version 4 run scripts, these run scripts are no longer supported. So, which means that you have to either use upgraded version 3 or directly use our latest version 4 run scripts. And the run script is the only thing that changes for different versions. So basically, version 2 uses an old way to define the problems. It's no longer supported. Version 3 uses OpenMDAO standard to define the design optimization problems. And it can be used with some minor updates or changes, which I will talk about that later. For now, if you haven't done so yet, please download the DAFoam workshop repository, which I'll provide a link here. Is this link, or you can Google search DAFoam workshop. It should be a repository. And then go to this workshop 2025 summer examples, Naga Level 12. And then in there, it should be able to see 2 run scripts called run script version 3 and run script version 4. And let's compare these 2 run scripts, and I can show you the differences. Let me share the screen with let me know if you cannot see the my VS Code. I'm showing version 3 and version 4 scripts. And the first difference is this task, this flag. The left-hand side is version 3, the right-hand side is version 4. Before, we called it OPT, run primal, run adjunct, check totals, like this. Now in version 4, we use this flag that is completely consistent with OpenMDAO, meaning that you have the options of run driver, which is the running optimization, which is to run the optimization. Run model means that run the flows analysis once. compute totals, it means that just run the adjoint solver once. And check total means that you compute the adjoint derivatives and then compare with the finite difference derivatives to verify the adjoint derivatives accuracy. And this task is fully consistent with OpenMDAO standard. That's the first difference. If you scroll down both scripts, the second difference is here. If you look at the left-hand side, in version 3, we call this objective function. If you look at the right-hand side in version 4, now we call it function to basically make it more general, because this function could be an objective function, it could be a constraint function, for example. So the next thing is that inside this function, you can see that the parts, before in version 3, we have defined different parts. Now it's no longer needed. So each function has only one part. And inside the part, and this add to adjoint, this flag is no longer supported. It actually is not needed, because whether to add this function to the adjoint will be determined by OpenMDAO instead of by this flag. Okay, that's the, I would say, third differences. And the fourth one is that if you are defining angle of attack, for example, you are doing an airfoil aerodynamic shape optimization. Your objective function is this one, drag coefficient. And usually you need to define a design variables called angle of attack. And then the drag coefficient needs to know your flow direction such that you can compute drag and lifts. You need to provide the name of your angle of attack variables. In version 3 this key is called alpha name. In version 4, I just changed it to a more general name called patch velocity name. And that's the fourth main difference. Okay, let's as you can see, that I will not run tutorials to actually run this case, but I will mostly focus on the run script differences. Okay, let me scroll down. The next difference is in how we defined the design variables. In version 3, we call it design variable, this key. If you look at the right-hand side in version 4, now we call it input info. Okay, again, this makes it more general and also make it more consistent with OpenMDAO, because OpenMDAO, each component in OpenMDAO can have multiple inputs. We call it input instead of design variable because some of the input might not be design variables. Okay, this is another major difference. The next difference, I'm reading if you can download this workshop slides, I'm reading these bullet points and go over this one by one. So the next difference is how we define the angle of attack variable. Let me show you. Go back to the scripts. In version 3, we have to define an angle of attack variable here. And also, if you keep scrolling down, and we also need to create a function to actually assign the velocity to the OpenFOAM field in this run script.py in version 3, which is the left-hand side. In version 4, this function is no longer needed as long as you define an angle of attack, which is right here. I call it patch velocity. In this input info, you don't have to define a function to actually assign value, because this is done internally in a new class called input DA input, which I will cover that later in the second part of this workshop. Anyway, this is no longer needed. This will save you some time to define these things. The last main difference is that we have a new way to define design variables for airfoil cases. If you scroll down, let me make it bigger. In version 3, the way we define the design variables is that we just add all the F50 points as the shape variables. And because this is a 2D case and it's symmetric in the span-wise direction, or the same as the span-wise direction, that's why we have to create this so-called symmetric constraints to basically link the displacement of the points at a two span-wise location, which is tedious. Say, for example, you have 20 F50 points. Only 10 of them are independent. The other 10 will be linked in the span-wise direction. And version 4, this is changed. We no longer use the, let me close this. We no longer use this way to define the design variables. Instead, we use a new function called shape function. Okay, so today I probably don't have time to elaborate on this, but the way it works is that you can select multiple points together. Say you can see that I select 2 points together, and then say they move in a y direction with the same amount of displacement. Okay, and this is much more flexible, and then it can reduce the number of design variables, and you don't need to define those symmetric constraints anymore, because you say that 2 points can move, 2 points in a span y direction can move. They are linked together. They move with the same amount of displacement. Okay. Any questions so far? Okay. If no, let's continue. And that's the main difference between the version 3 and version 4 round script. Let's go back to the slide. As I mentioned, there's a major difference in the way we define the design variable, which is called input info. Okay, so this input info's interface changes quite a bit. That's why I want to elaborate on this new interface called input info. Basically, we define all the inputs for the solver component, maybe for the function component. To look at the difference, and please check the run script test input info.py in example NAGA 12, which I will open it from here. This is the file. So let me close this too. Okay, so if you scroll down, you can see that this is essentially the NAGA 12 script. Okay, but I give you an example of how these input variable can be defined in this input info key. So, for example, the first input is called arrow volume coordinates, and the name of this this key is the name of the input for the solver and function components, which means that by doing this, you will be able to add an input called arrow volume coordinates into the solver and function component, which I will show you here. Let me open the N2 diagram of this problem. Let me make it bigger. Yeah. And this is the N2 diagram of the script I just showed you. Okay. So by defining a key called arrow volume coordinates, a key called beta, a key called FV source, a key called UN, essentially, you will be able to add 4 inputs to the solver component. And this is, well, this is not a key. So let me run the case and generate a key. This is the old keys, but so I haven't shared you my terminal yet. Let me show you my terminal. Hopefully you can see my terminal here. I open the doc image. You don't have to follow me. I just want to show you the steps, how I can generate the N2 diagrams. And so I'm now in the 2025 summer workshop. I go to the examples. I go to the NAGA 12. And I basically run this case. Test. And the task is run model. So I run the flow for once. And by running the scripts, it will generate the N2 diagrams. Then you can see the connection. You can see how many components are in this province. Yeah, let me maximize this window. And you should be quick. Okay, the flow is finished. Now we can look at the N2 diagram of this problem. So let me make it bigger. If you remember, as I said, when you define these 4 keys in the input info key, so it will add those inputs to the solver component. By the way, this is the OpenMDAO N2 diagrams. This blue color represents groups. This cyan color is the components in OpenMDL. This greenish color represents the input for components. You can see that by defining those keys, we essentially add those 4 inputs to the solver components. We also add those inputs to the function components, which is defined here. So you define the input, you say which component you want to add this input to by using this component key. Okay, and you might each input has a type. For example, this one is volume coordinates, and this type is field. This type is patch variables. These types are the preserved names, which will be, I will talk about that later, which will be defined in the DA input class. So basically you say, this is the input name, this is the type of the inputs. I want to add it to the solver and function component. And this beta is a field inputs. You can define other relevant keys. For example, this fields, the name in OpenFOAM is called beta field inversion new tilde. It's a scalar field, and it's a non-distributed variable. Okay. So by doing this, if you define a key or an input for this for the solver, you don't need to redefine that later. So you can directly use that. I will show you this feature later when we are doing some developments. Okay, that's the one last thing I want to highlight is that once you define this, and you can see that they are the inputs for the solver component. But one more thing you need to do, you need to create the same input for the design variables and connect, for example, this beta from the design variables components to the inputs of the solver components, right? This is where we define it. Once you define that here, if you scroll down and this self DVS, again, I assume that you are familiar with version 3. This self DVS essentially they are so-called independent component in OpenMDL. They are essentially the design variables OpenMDL can directly control. So you need to connect these design variables, for example, called beta, to the scenario beta. Okay, what's this scenario? This scenario, if you go back to the N2 diagram, the scenario is here. This is the solver group scenario. So essentially connect this beta design variables to the solver's beta. You may ask, hey, why do I want to connect this? Because in the design optimization, OpenMDL only control this beta here from the design variable components. And once OpenMDL changes the design variables, DVS beta values, you want the change to get propagates to your solver and to your function component. That's why you need to connect these two. So OpenMDL does not directly control the beta from the solver's input. Instead, it controls the beta from here. Okay. So you need to connect. That's how you need to connect. Why you need to connect beta to the scenario beta 1. Similarly, and if you define a shape, you need to connect the shape to the geometry.shape. If you define some other field variables, such as velocity inlets, you have to connect this velocity inlet from the design variables component to the scenarios component. Okay, and this is the same with the same. It's the same thing in version 3. We also do that. One last thing I want to highlight is that please carefully define those input to avoid conflicts. For example, if you defined the angle of attack, which changed the velocity at the far field patch, and later you define the second input, that is the far field velocity, they both change the velocity at the inlet. This will create big problems. Please avoid that. Okay. Okay, that's the input info. If no more questions, I will continue to go back to the slides. The next thing is the MDL interfaces, and this change is very, very minor. And let's compare the run script version 3 and run script version 4 for the mock tutorial wing case. Again, this is an aerostructure optimization for a 3D wing. And now I'm trying to open the version 3 and version 4 scripts. I'll put us side by side. And again, left-hand side is version 3, right-hand side is version 4. So it's only the change is very, very minor, just only one change for MDO problems. So before, in version 3, we have a coupling info, this key that defines aerostructure coupling, aerothermal coupling, aeroacoustic coupling. Now this key is changed to basically we move this information to the input info and output info. Okay. Again, now you see the reason we define these two keys. Again, we want to make them general, meaning that as long as you define, for example, output info. So I define a new key called F aero, which is the surface force from aerodynamic surface. Could be a wing, could be some other aerodynamic surface. And then you connect to the force coupling component. Again, this force coupling component is a special component that is used only in aerostructure coupling. What it does is essentially it takes the state variables from the aero component, it takes the volume coordinates from the aero component and extract the surface force. And this surface force will be passed to a structure solver later, which doesn't handle structure solver. So at this moment, which we will use text. So, and here's how you define this F aero. You no longer define it here, instead you define an output info here. And that's essentially the main difference. And we use a very similar strategy for aerothermal coupling. Again, the purpose of doing this is make this interface more general. Okay, that's the only difference for the MDO province. I will go back to the slides. Next. We also have a new interface for unsteady province. Before, if you remember, we can run unsteady optimization only using version 2 scripts. We cannot use OpenMDAO-based scripts. Now this problem is fixed. Let's look at an example of the version 4 unsteadied optimization script. Version 4 is here. Let me close these. I don't need these. And this is an unsteadied aerodynamic shape optimization scripts for version 4. You can see that mostly, for example, this DA options is very similar to a steady state script. The only difference is that first you have to define, hey, I use an unsteady solver, say DA pimple form. For unsteady solver and unsteady optimization, you also need to define unsteady adjoints. Some parameters you have to define here. If you keep scrolling down, the next difference is here. So if you are doing steady state design optimization, your objective function will, by default, we will take the value from the last iteration. So if you are running steady state simulation, we assume that for the last iterations, the objective function has already reached an equilibrium state. It will flatten out. But for the unsteady case, you can define a new key called time OP. We call it time operator. So you can say that this CD in the unsteady optimization, we want to use the averaged. In this case, obviously, it's time averaged CD as my objective. We have some other options, such as the maximal. Sometimes you want to take the maximal values from your CD time series and use that as the objective. So this is the second main difference. I noticed that I haven't put these points into the slides. Maybe I will add it later. The third difference is that for the unsteady optimization, you need to define a key called unsteady component outputs. Okay, so then because the unsteady simulation optimization will not directly use the function from this key as the optimization. Instead, you will look for unsteady component outputs. So you can only pick the component output you define here as your objectives in unsteady optimization. Here I defined a key called objective function. It includes only one variable called CD. I saw somebody have annotations here. Is there a question there? Okay, if not, can you erase this? I don't know how to erase this. Annotation. Yep, got it, fixed. Okay. Okay, no problem. Okay, let's continue. So, and if you define more keys here, for example, and you can define CL And then your unsteady obtundation will use the CD plus CL as the objective. So this is just a way you can combine multiple objectives together. The reason we define this is that we don't want to solve the unsteady adjoint twice, right? So you can just add them together. This will be very useful for unsteady field inversion. Okay, that's the second, that's the third difference. The next difference is that we defined so-called new builder, which I will talk about what a builder is, but a special builder for unsteady problems. Basically, we treat this component as an explicit component. Okay, so in OpenMDL, for steady state case, we usually treat the solver as an implicit component. So, and the rest of the script will be very, very similar to a steady state. And the last difference is that in unsteady cases, and we promote all the variable names. For example, when you want to use the shape variable, you don't use it as geometry.shape. Instead, you just call it shape. And this just facilitate the connections. And that's the last main differences and for the version 4 script. Any questions so far? I think that's the last slide for the user features. Today I want to focus more on the developer features. That's why I go very quick for the first section. Okay, if no more questions, yeah, we have all these new scripts updated and upload to the DAFoam tutorials. If you're interested in running one tutorial, please go check that repository. It has the latest version 4 run scripts. And maybe a few of them are still using version 3. And if you find that any of the run script or any of the tutorial is not working, please let us know. Okay, that's the first part. Let's go to the second part. Developer-focused updates. Actually, this is the main update. From a user perspective, you probably won't be able to feel a lot of differences if you're just a user. But if you are a developer, and can see that the DAFoam code structure changes quite a lot. And the objective here is to make the DAFoam development easier. And before I talk about the details, I want to show you this table that summarizes the main improvements in version 4 development environment. This column is version 3, this column is version 4. And one of the main things is that if you want to compile DAFoam repository, right, for the first time, in version 3, it may take 30 minutes. In version 4, it gets reduced to about 10 minutes. The reason is that in version 3, we have to compile 3 libraries for incompressible flow, for compressible flow, for solid mechanics. Right now in version 4, we combine all these libraries into one library. That's why we can directly reduce the build time by 60%. We cut the build time. And that's one of the main things. But the thing I want to highlight is in the second row. If you want to rebuild DAFoam, meaning that, for example, which I will show you later, if you are a DAFoam developer in version 3, you know that even though you make a very small change, and when you need to recompile DAFoam, you need to recompile everything, which again will take about 30 minutes. But in version 4, we completely restructure the code such that when you add a new feature into DAFoam, you only recompiled the new codes. And then this recompiling process can take maybe less than 1 minute. A lot of times it's just 30 seconds instead of 30 minutes. That's the main improvements in version 4. Okay, we made a lot of changes to make this happen. Again, developing in version 4 will be much easier than version 3. So other improvements include, for example, the build commands. In version 3, you have to run multiple commands. In version 4, it's just one command to build DAFoam. In version 4, you can use maximum available cores to build DAFoam. You will compile very, very fast on HPC because you can use like 20+ cores to build DAFoam. And this has been covered. And also, we standardized. If you want to add a new design variables, add a new objective functions, add a new inputs, add a new positive derivatives. Before in version 3, you have to add multiple functions, kind of ad hoc. But now in version 4, everything is standardized. For example, if you want to add a new design variables, right now you just add a new function and that's it. It will be much easier. These are the summaries of our improvements in DAFoam version 4. Okay, what will happen next is that I will very briefly talk about the overall code structure in version 4. Many of the structures are the same as version 3, but I just want to let's review it again. After this, I will show you some hands-on examples. For example, if you want to add a new parameters in DAFoam, how would you do it? If you want to add the new design variables, we will have some hands-on examples. But before that, let's review the overall code structure of DAFoam, which will be important because depending on your needs, sometimes you can just add a new feature to the C++ layer. Sometimes maybe just add a new feature in the Python layer. That's why I want to review again what are these layers in DAFoam. DAFoam has 3 layers: C++, Python, and Python. Okay, that's from a coding perspective. So the C++ layer, essentially, it does most of the actual computation, including solving the flow, for example, compute the surface area, deform the mesh, and such and such. Okay, so this C++ layer, and by the way, if you are not very familiar with this diagram, this is called DSM diagrams. The diagonal blocks are the main components. The off-diagonal blocks are data transfer between the components. One component, this green box, takes input from the vertical directions in the compute. It outputs some data or files in the horizontal direction. For example, if you look at the C++ component, this C++ layer, it would take some OpenFOAM libraries. Okay, and also the DAFoam source code, which is in DAFoam source adjoint. And then it would compile those and then generates a few C++ libraries called DASolver.so. Okay, these are pure C++ libraries. Of course, it also depends on OpenFOAM. They cannot be directly called in Python. That's why we need an intermediate layer called Python layer. This Python layer does nothing but wrapping these C++ libraries into the Python format, which means that the Python layer doesn't do any computation at all. It will just take the C++ libraries along with some wrapper interface, which is in DAFoam source code PyDASolvers. You compile these things and output a Python library, which is callable by Python, which is called PyDASolvers.so. You will save this PyDASolver.so into these folders. By the way, the C++ layers libraries will be saved in this folder. Okay, then in the Python layer, which most of the user will interact with, will only read this PyDASolver.so along with some other Python classes, which are defined in PyDASolver, PyDAFoam.py, and MVis.DAFoam.py, and then to do actual optimization. Again, these 2 files, along with this library, when you want pip installed, it will be saved to this directory. Okay, how that's the overall layer structure in DAFoam. Again, I want to highlight that the C++ layer does most of the computation. Python layer is just a wrapper. The Python layer, sometimes they do some computation, but very lightweight computation. Just one easy computation like copy paste or assign value to a vector, this kind of stuff. But for any other computation, we usually do it in the C++ layer. That's why, depending on your need, if you want to add new features, you need to decide, should we add in the Python layer or C++ layer? Okay. All right. So after we talk about the new layer structure, I want to highlight a few new features in version 4 layer interactions. The first one is that before, if you remember, if you are a version 3 developer, in order to pass an array from Python layer to the C++ layer, we have to first convert this array to the PESC format, which is not very easy to use. Right now in version 4, we can directly pass a Python array from the Python layer to C++ layer, which makes this data transfer much easier. There is no need to use passive vectors or matrices as input and output. If you click this link, you will be able to go to a specific example. For example, maybe it's too small for you to see. Let me zoom in a little bit. Now, this is just a Python wrapper that will take a NumPy array from Python and pass it to the C++ layer. So this is the format. So we use this format to pass the Python array directly from Python layer to the C++. Okay. So the second bullet point I want to highlight is that before you can, the Python layer can call the C++ layer functions. So you can manipulate how you want to run the flow, how you want to define the mesh, how you want to output flow fields, and such as how you want to solve the adjoints. You manipulate this C++ function mostly in the Python layer. In version 4, we add a new feature. The C++ layer can also call the Python layer's functions. And this, most of the time, you probably don't need that, but sometimes you do. For example, in the field inversion machine learning, sometimes you want to call the TensorFlow from Python layer in your C++ layer. For example, you train a neural network models, you save it to the disk. You want to load this model in, and then call the neural network models, which is written in Python, in the, for example, TensorFlow or PyTorch package. You can call those functions in C++ layer right now. We call it callback function. Again, I give you an example here. If you click this link, you should be able to see, for example, here is a C++ DA regression.c. This is a C++ layer function, and we can call the Python function. So here it calls the Python function, callback function, to actually call the TensorFlow's predict function. This is a very useful feature if you want to do the callback. The third feature is that we no longer separate incompressible flow, and solid mechanics. All these conditions are combined into one library, which is called library DAFoam.so. Okay, everything's combined together. Okay, so now what I want to do next is that I want to, before I go into the details, I want to show you the Python layer structure. Today, if you look at the layer structure, right here, we have C++, Python, and Python layer. Today, I probably don't have time to talk about the details for the C++ layer, which will be much more complicated. But we do have some time to talk about this Python layer, how we manipulate the C++ functions for design and optimization. So let's look at this DAFoam's Python layer. So one thing I want to highlight, main entry points, if you are a new developer, you want to get started, and this is the place you can get started. The main entry point is called the DAFoam builder class, located in the DAFoam/emphasis/emphasis.foam.py. Okay, so let me click this link. I believe we will be able to go to this function. Okay, now I will just show you what this function, but this is the very first class, and this and it's emphasis DAFoam.py. This is the main entry point. Why? If you look at, I go back to the run script, right? And this is no, this is not a good run script. Let me give you a different ones. Let me give you the Naka 12 run script. In the run script, if you scroll down here, we initialize this solver first in the setup class. That's why this is the main entry point. When we initialize this class called DAFoam builder, we provide some DA options, which is defined here. What options do you want? We have many options. We also provide the scenario names, the mesh deformation options, and then it called builder initialize. That's why that's the very first class we initialize in the run script. So let's look into this class. Let's see what this class is doing. Okay, so let me scroll down here. If you scroll down, you can see that it takes some options from your run script, mesh options, scenarios, these options, and then save them as the class variables. But if you keep scrolling down, you will see an initialize function here. Let me see if it's good. Yeah, should be good. And then in this initialize functions, and we call it this line. This line is critical. That's the very first line we initialize the C++ layer. We basically call this PyDAFoam class, which is defined in a different directorate, which is not quite important. But this class, essentially what it does is that it initializes the C++ layer. By saying initialize, I mean that it will allocate the memory for all the flow variables, including velocity, pressure, density, and such, and allocate the memory for the mesh points, surface area, and such this variable. This is the main call at the very first call, and if you want to initialize the C++ layer in the Python layer. So, and then we save this class, this object as self-DASolver. Once you have this solver, you can call many of these functions, right? DASolver, the set mesh, print family list. You can do a lot of things. Okay. And by the way, these set mesh, print family lists, some of them are Python functions, some of them are actually C++ functions. Okay. Again, this is the very first thing we need to do, initialize the C++ layer here. Then keep scrolling down. You can see that this DAFoam builder also provides quite a few functions or interface, and all the rest of these functions will be used by MFIS. Again, what is MFIS? MFIS is OpenMDAO-based package that facilitates a high-fidelity MDO, meaning that the high-fidelity coupling between, for example, computational fluid dynamics solver and a finite element structure solver to do error structure optimization. So from a solver perspective, all you need to do is just expose some common interface to MFIS, and MFIS will handle the rest for you. And this interface are listed here. So the very first interface gets solver. So you just essentially intend the object, your C++ layer object, DASolver to MFIS. This is very straightforward. The second one, again, it's a standardized interface called get coupling group subsystem. So, and as you probably know that in OpenMDAO, a group contains many components, right? And then here, one MFIS say, okay, get the coupling groups, and then we will return the DA group, this object. This is the class, which I will talk about later. Okay, of course, by providing some parameters. So DAFoam group, and so we have a new chats. Let me read the chats. Can I just check into be set MFIS? We see the wrong script. Oh, okay, that's a good question. I got a question in chat saying that, do we need to change this MFIS underscore DAFoam.py? No, we don't. As the user, the only thing you need to change is the run script.py. So you shouldn't change this MFIS underscore DAFoam.py. If you are the user, you don't want to change DAFoam at all. Here, I'm focusing on if you want to change something. Say, for example, I want to add a new discipline, I want to add a new solver, I want to add a new object functions, then you need to change this script. Okay. Okay, here I just want to go very quickly about to show you the overall structure. This DAFoam group, then let's look at what this is. Let me show you the N2 diagram. And this is the DAFoam solve coupling group right here. Okay, so essentially it's the solver. The screen share. Okay, so no, I think I share you the. No, I'm not showing you the wrong script.py at this moment. Let me see. I'm just showing you the MFIS DAFoam. Yeah. So then we can go to this. Here you can see that we can. just want to confirm, can you see my web browser? Oh, my bad. Thanks for reminding. I realized that I haven't really shared my web browser yet. Now I think you should be able to see my web browser. I'm showing you the emphasis/DAFoam. Great, thanks. So as I mentioned, maybe I can go back a little bit. This is the DAFoam builder. This is the place we initialized the C++ layer. This is the place we initialized the DAFoam group. And this DAFoam group essentially is this guy. It's this guy, the coupling group solver, because we don't have any other. If you have any other coupling disciplines, you might have more components in there, but for the aerodynamic only case, we have only one solver. And then what's next is that get mesh coordinate subsystem essentially return the DAFoam mesh. And the N2 diagram, this is this component. Okay, I'm just trying to link the N2 diagrams to this file such that you know that where this component is added to the system. If you keep scrolling down, get pre-coupling system. This one is essentially this guy, Warper, the mesh volume mesh deformation called aerial pre-coupling. This is the place where we deform the volume mesh. Okay. If you keep scrolling down, we have the post-coupling subsystem, which correspond to this guy function. You can see that what this DAFoam builder is doing is to add those components in groups into OpenMDL. Then you should be able to see these N2 diagrams and the coupling. I want to highlight that, as you also see in the slide, is that the geometry component, which use PyGeo to deform the design surface geometry, is not defined in here. Instead, it's defined in the run script. For example, this geometry component is not defined in this DAFoam builder. Instead, let me show you what is defined. It's defined in the run script. I assume that you can see my run script. You can see that we add a subsystem geometry. Here, we add in the run script. The reason this is designed like this is that the geometry can be completely independent of the DAFoam. So it's a standalone components. You can add it in your run script. But the DAFoam will handle the scenario one. Every components, groups, input and output, and this block will be handled by DAFoam. And this block, you add it in the run script. This mesh, add it in the run script. Design variables component, you add it in the run script. Okay, that's the overall layer structures in DAFoam. So yeah, I have already covered this. Any questions so far? Okay, if not, what will happen next is that I want to have like 5 minutes break. Okay, so then next we will have some hands-on examples on how to add new features in DAFoam version 4. For example, how you can add new parameters, C++ function, object function, design variables. For that, we need you to have DAFoam compiled. You can either use Docker image, or you can compile DAFoam from scratch on your computer. So please get that ready, and also please download this DAFoam workshop repository, because in this repository we have a few examples. We will use that to showcase how do you do these things. So let's have a 5 minutes break. Let's come back at, right now it's 10:52 US Eastern Time. We will resume at 10:57 again US Eastern Time in 5 minutes. Okay. So Diego, if you're still there, I can show you how this is done. I got questions from the chat and how to generate the dependency matrix. So I'm showing you an example of the run script Nakatomo 12, and this is a very standard run script. If you scroll down, and there's a place line, for example, line 183. There is a line called openmdl.n2, and basically you say, I want to generate this dependency matrix. The name of this dependency matrix, emphasis underscore n2.html. Then you can open it in HTML. So once you define a problem, the problem has no error. When you run the scripts, it will automatically generate this HTML, which means that next, I will show you how to run this case. You should be able to see this file generated in the case folder.
Thank you, Dr. He.
Great. Andrew, are you still there? So I got a question about solvers. Yes, we can add those back. We remove those solvers in version 4. That's right. So I will note this, and maybe Leon, can you note this down? And we need to add this this DA scalar transport form solver back. Yeah. Or if you you can also submit an issue, request this feature, and it's true that we delete some of the functions, some of the solvers, some of the maybe turbulence models in version 4. We will eventually add them back. But thanks for the note. Yeah, let's wait for a few more minutes, and we will resume maybe in about 1 or 2 minutes. Yeah, I also got a questions on the chat that if you are a new user, would suggest you check the DAFoam website and go through some tutorials because this workshop is for more advanced users who have already used DAFoam before, but I want to focus on the new features. And you can also check we have 2 previous workshops, especially the 2021 workshop covers a lot of basics about how for first-time user. Also, we are building a new website tab or section about user guide, and these guide will be hopefully will be useful for new users to get on board and get proficient in using DAFoam. Yeah. But right now, as of now, I suggest you check the website and go through some simple tutorials such as Nakada Virtual Aerodynamic Share Optimization. Okay, let's continue. Again, this is the second part of this workshop. I want to have some hands-on exercise or example or tutorials that can show you how do you add. We might not have time to go over all of these, but hopefully we can finish as many as we can. Okay, let's get started. Let's open your terminal. So what I'm going to do now is I'm going to put the slides and my terminal side by side. Okay, let me know if you can see. I'm showing 2 windows. On the left is my PDF slide. On the right is my terminal. So please download the DAFoam workshop repository. Okay, so if you haven't done so, please do that. Then open a terminal and CD into the. Let me exit this first. So I download it to my desktop. That's why I CD into the desktop. And my workshops in 2025 summer. Okay. Great. Once you have done that, what's next is that, so go into this folder, type ls, make sure you see this, okay? You're in the right directory. What's next is that create a DAFoam Docker container. Remember to use version 402. If you don't know how to create a component using Docker, please click this link. There's a link here. It will link to this command. You are using Windows 10. This is the command. If you are using Mac, I'm using Mac. I basically copy this command. Okay, this entire command and paste it here and hit enter. What this command will do is that it will create a DAFoam environment for you, which is pre-compiled. You don't have to compile again. Also, it will link this 2025 summer folder to your containers mount folder, which basically create a link between this container and your computer. Okay. Once this is done, type ls. You should see that in this container, you should be able to see these examples in slides folder. What's next is that this container has a pre-built DAFoam. Let's find it first. If you look at the slides, it's right here. You can CD into this directory. So there is a typo there though. So should be CD home DAFoam user DAFoam repos and DAFoam. Okay, so basically you CD to a home directory, you should see a folder called DAFoam. Inside DAFoam, you should see a folder called repository repos. Go in there, and the repos you should see a folder called DAFoam. Yeah, this is not very obvious, but you should be able to in this directory first. So the path is this. So obviously there's a typo here. I need to fix it. Liam, please note this down and update the workshop slide. Okay, once you're in this, you run this command, make. Okay. And what this will do is essentially compile DAFoam. And this is the only command, only command you need to compile DAFoam. You can see that it really doesn't compile anything. And because the version I have in this image is already pre-compiled. And DAFoam will check every file. If every file is compiled, it will just skip it and then pip install it for you. It will, at the end, you will print out a summary of all the libraries it get compiled and get pip installed. And you should make sure you see this build successful, this message. Otherwise, your source code may have some problems. Okay. Is there anybody following this and managed to see this build successful? Let me know if you need me to slow down a little bit or have any questions finding DAFoam or compiling if you get an error or something like that. And I expect this section will be very interactive. Again, stop me at any time if you have any questions, and remind me if you want to send a question in the chat, which is okay too. Okay, as I mentioned in the slides, that do not run all clean. Okay, in version 3, if you remember, we have to run all clean and then run all make. In version 4, please don't do that, because we have a mechanism that automatically check if this file is changed, and then if it's changed, we will recompile that file only and without compiling the whole library, which will take about 30 minutes. Okay. Next, what's next is that we are going to do the first change existing functional variables in the C++ layer. I assume that if you want to change some Python layer functions, it should be straightforward, because just go straight into the emphasis_dafoam.py or py-dafoam.py. You just directly change that, run a pip install, and then you will copy the files to the DAFoam module. You can use it directly. What I'm showing you right now is that if you want to change something in the C++ layer, what you should do. This is the very first, very simple case. Essentially, it's the hello world case. So first go into there. I'm already in here. Then let's modify this file, DASimpleFoam.c. You can use this command vi. It's in the source adjoint DASolver DASimpleFoam.c. Okay. Let me move this out a little bit in case you can't see it if it's at the very bottom. Okay, so again, I assume that you're familiar with Linux command. This vi is just a way to view the file and modify the file. So if you're not very comfortable with using this, all you can do is copy this file. For example, if you say, oh, I don't want to modify this file, I can show you how to copy this file. Copy this file to the mount directory, this mount directory. Okay. So then you should be able to see this file if you go to your 2025 summer workshop, and you should be able to see this file. You can open it. For example, I open it here using a text editor. You can modify a file here. Okay. After the modification is done, you can copy it back to the mount DASimpleFoam, back to the source adjoint DASolver DASimpleFoam. You can copy it back to here. Okay. So, but I prefer the first approach, just directly add it in Linux using this vi command. Show you this. And what do we want to add it? So once you are in this file, scroll down or go down to a function called run primal. Not this one. Keep scrolling down. Solve primal. Okay. So go to this function and go to the bottom of this function. Yeah, right here. Right before the return. Let's press I to insert some command. Let's call it info. And print something such that you can see it. Okay, info is just a print command in OpenFOAM, and this ENDL means that line break. Okay, so we basically add this, which means that when we run the solver, after it's finished, we will print out this message. Okay, after this, press escape, :WQ to save this changes. Okay, so once this is done, just remake DAFoam. Run this all make command, and that's it. Because you change anything in the C++ layer, you have to recompile DAFoam. So if you remember, if you are a version 3 users, this process can take 30 minutes. Now, because we are using version 4, you can see that you only recompile this DASolver.c, DASimpleFoam.c. You just modified without recompiling all the other files. This would save a lot of time. And my computer is not very fast, but usually if you just change one file, recompiling this can just take 30 seconds. So you can see that it first compiled the original version of DAFoam, and then it compiled the AD version, compiling ADR, the reverse mode AD version of the DAFoam, all in one command. After compiling this C++ library, you will run the pip install command for you as well. Again, this is just one command to recompile everything. Let's wait for a while, and the compilation is finished. Okay, now we're just running the pip install. Again, you should see that build successful, which means that your change is successful. Otherwise, if you get an error, you won't see this message. Now, it seems that I managed to recompile, add a new print statement to my solver. How do I know if it's working? Let's go to this bullet, cd into this folder. Home, months, examples, DAFoam. That's the DAFoam workshop repository. Right? So I have an example here. So DAFoam, and so if this is the first time you run it, you'll probably get a permission error. That's why you should run this command first to give the right execution permission for all the files and all the folders in this directory. Okay, so let me run the all command first. Let me start from scratch. So before running it, you should see this. Okay, then run this command to give the permission. You type ls. You probably see some green color, which means that, okay, this file, you have the permission, and then run this pre-processing.sh, which essentially generates the mesh. Yeah, the mesh generation is done. What's next is run this command. Version 4, text equals run model. Or you can copy this command and paste in your terminal. And then if you run it, it may take a while to get started. But essentially, you will run the flow analysis. Remember, you add a print statement at the end of the solver. The run primer process, you should see that print statement. Yeah, here it is. Here's how you add a very simple hello world print statement to the C++ layer, and then you will be able to see it when you run the new solver after recompiling DAFoam. Okay, has anybody managed to reproduce this? Okay, great. I got a thumbs up. Nice. Okay, then let's continue. That's the very, very simple things. Obviously, you need more than that. That's why let me show you another example. Say sometimes I might want to add a new parameter, because if you remember in the runscript.py, we define a lot of parameters in the DA options, this dictionary, right? So sometimes you might want to add a new option or new parameters, new variables into this. And this is an example how you should do that. Again, go to this folder. This is the DAFoam source code folder. Use the via command to open the this file. Open this file. I just copy PyDAFoam. All the options are defined in this PyDAFoam file. This is a Python file, so okay. Then you can scroll down. So you should see a class called DAOption. Okay, all the parameters options are defined here. Keep scrolling down, you see that we define a lot of options, and you can go to any place in this DA option in this initialize function. Say I go to here, right below the self solver name, I define a new option called self test option equals 3.0. Here is a critical part. You need to give default values for any new options you create. If you write it like this, test option equals 3, and DAFoam will think that this test option is an integer. If you want it to a float number, you should give an initial value of something like this. Because I want it to be a float, and then or scalar, then I give a default value of 3.0. For all options, you need to give default values, including the lists, including the words, scalars, or integers. The only thing you don't need to give default value is a dictionary. So if this is a dictionary, you just give an empty. Of course, you can give some default value as well, but you don't have to. But here, I'm showing you how to define a scalar option here. And that's it. After this, escapes, :WQ to save it. Okay, once you add this new option into this file, it's ready to use. Okay, you can use it in the Python layer, but here I can show you how to use it in a C++ layer. The way it works is that when you add this option in here in this PyDAFoam class, you will pass these options to the C++ layer such that you can read it. Now let me show you the process how this can be done. Again, please open this file, the file we just modified in this directory, source adjoin DASolver DASimpleFoam. I just VI and copy and paste. Okay, this is the file. You can see that we just modified. We just had a hello world example. Now modify it, add this inside. Copy and paste. Of course, the format is not very good, but fortunately, C++ is not very picky about the format. Let me explain what these two lines are doing. First, it creates a scalar, which is the data type in OpenFOAM called test option, and then you will read these options from the DAOption class. Okay, so remember we added in the DAOption class. Get option, this option is a scalar. Oh, you always need to prescribe the type of this option. The option's name is called test option. This name should be consistent with the name you define here. Okay, then you print out my test option is print out the value. Okay, after this is done, :WQ. Again, recompile DAFoam or make. Again, this will take about 30 seconds. While it's compiling, let me explain more how the options works in DAFoam. The options we just defined is in here, PyDAFoam.py, right? So we give a default value. If you don't change the default value, of course, you will use this 3.0. But in the runscript.py, we can change its default value to a different value. So we should see that when you run the solver, you will print out the value you prescribed. Okay, we're going to test this when the compilation is done. We're going to first run it without defining anything in the run script. You should see that it print out 3.0. And then we will define some other values in the run script. And you should see that you should print out whatever value you prescribed. Okay. Now the compilation is finished. Let's cd into this folder. Copy, cd, and paste. and then run this command. Copy, paste. So remember, we should print out something at the end of the simulation. Let's see if it does print. Okay, great. Hello world is printed. My test option is 3. Right, this is working. So we managed to add options in a Python layer and pass to the C++ layer and print out this value. Of course, let's go to this bullet point. We want to do more. Can we change the value? So now, view the run script, v4. Change this file. So in this file, we change the value for these test options. You should define in the DA options. I can define it as my first key. Test options equals 15.2. Right, so I will give a different value in the DA options, and then this value will override the default value and get passed to the C++ layer and get printed out. Let's see if this happens. After you add these options, QW, save, and then run this command again. Python run script v4 test equals run model. Okay, you can see that this value get changed to 15.2. So which means that this mechanism is working. Has anybody managed to get this to work? All right, nice, Andrew. So I have a note here that just one thing you want to keep in mind. Sometimes this could be very confusing. The DA option defined in run script will be passed to the C++ layer only once, when the DAFoam is initialized. Just keep this in mind. If you need to pass the DA option from from Python to C++ again, you need to manually call this update DA option class. If you click this link, it will give you an example. So this most likely you don't need to use this feature, but sometimes, for example, in your run script, you call the flow twice. For the first time, you use test option 5. For the second time, you change the test option to 6. And the second time you called the flow, it will not use the new value because, again, as I mentioned, all this option will be passed to the C++ value, for the C++ layer only once, when the DAFoam is initialized. If you want to change this option later down the road, for example, at the first iteration, at the fourth iterations, you suddenly want to change this value, you have to call this function to pass these parameters to the C++ layer again. And just keep this in mind. Okay, let's go to the next. Now we know how to print a simple statement. We know how to add new options to the C++ layer. Let's try another thing. Add a new function. Okay, add a new C++ function and expose it to the Python layer. Because most likely we want to add some more complicated function, not just print out a value, not just pass the parameters. For example, we want to, from the Python layer, we want to know the mesh size, for example, how many mesh cells you have. We want to know how many faces you have, or we want to know what's the mesh quality, what the mesh quality is. Then, in this case, we are talking about complicated things. Then we need to write a function. So in this example, I'm going to show you how do we define a function in C++ layer and then expose to the Python layer, meaning that we can call this function, new function, in the Python layer. So the overall process will be like this. First, we go into this DAFoam source code, of course, cd into here. And then view this file, copy this file. So source agent.dsolver.h. And this is the only interface that link the C++ layer and the Python layer. So this DAFoam is a very large file, and you can scroll down to the public member, not the protected ones. Keep scrolling down. Yeah, the public member, you can add a function somewhere, public function, yeah, add it here. Line 206. You can essentially copy this line, these few lines, copy and paste here. Yeah, I will forget the format. C++ is not very picky about format. Anyway, you can see that this is a function called print mesh size. Okay, it returns nothing, but it just print out something. When you call this function, you will first call the OpenFOAM's internal class called mesh.number of cells. This is an OpenFOAM command, OpenFOAM function. It will return the number of cells, and then it will print it out to the screen, something like this. It's slightly more complicated than the previous two tasks, but still shows you a very minimal example of how you can define a function. Now, this is no longer a parameter, instead it's a function. Once you add this to here, you can colon WQ. Okay, and then the C++ layers implementation is finished. But we cannot directly, as I mentioned, we can't directly call it in Python, right? We have to write some Python code to link, basically wrap this C++ function. The place we define this Python codes is here. Copy this line, view it. And this, you can see that this folder called PyDASolvers. These are Python functions. And then once you're in this file, you can scroll down to the public function somewhere here, for example, line 62. And then copy this block of the code and paste here. Again, I ignore the format, which is fine. You can see that this function is essentially just call the print mesh size function you define here. Okay, just provide an interface. You can follow the format from other wrapper. This is essentially a wrapper. It doesn't do any computation. Okay, and then you can save it. Unfortunately, we have to modify another file, another Python file here. We have two Python files to add here. Then we modify a second Python wrapper file called pydasolvers.pyx. And this file, this is a very long file. Again, this file, this class or this function or this module doesn't do any computation. You just wrap your function. We need to add this wrapper to two places. One is in the C. Well, let me maximize this window. Otherwise, it's really hard to see. The one place is add to the CPP class to declare this new function. Okay, so you should scroll down to about line 56. In this file, the format does matter. Make sure that you have the correct formats. So copy this because it's a Python file. So to line 56. And this CPP class, basically you declare there is a Python wrapper function called print mesh size. It's return void. It doesn't return anything. And then keep scrolling down. So I need to go to the next page. So keep scrolling down to the class, to this class, PyC definition class. For example, I can go to line 147 space and then copy these lines, paste it here. Now the format does matter. You make sure you have enough space. 1, 2, 3, 4, 4 spaces. Again, this you can see that essentially a wrapper. You just call this print mesh size. Okay. Okay, then save this file. And then the wrapper is finished. The C++ layer implementation is ready. The wrapper class is ready. Now we can call it. The way we call it, there are two ways we can call it. And one way is that we call it in this DAFoam. Okay, so we can open this file. This is a Python file, right? We want to call that function in a Python file. Let me show you what's the best place. Show me this paste. Yeah, remember you add option here, but now we can scroll down to find the function call underscore call. So for now, I won't be able to scroll down. I will just search for it. Right. So if you are familiar with VI commands, you can do / search keyword. You will be able to find this. Okay. And then in this function, scroll down to the end of this. At the end of this file, at the end of this call function, print out mesh size. Of course, you can call this C++ function anywhere in the Python layer, but where I want to print it is at the end of the primal simulation. Okay. So remember, this is not printed in a C++ layer. Instead, I printed it in a Python layer. This Python layer will call C++ function. Okay. So then after this, save this file, and then recompile DAFoam. So to summarize, we made 3 changes. The first change is in the C++ layer. We add a new function to implement something. For example, print mesh size, to implement anything you want. That's the first thing we need to change. The second thing is, once the C++ library is ready, we add something to the size layer to create this wrapper. So we need to add 2 files for this wrapper. One is called DASolvers.h, the other is called PyDASolvers.pyx. You can follow the format in there. Okay. After these 2 steps are done, and this wrapper is ready to use, then you can call this C++ function in any Python file. You can call it in PyDAFoam. Later I will show you can even call it in a runscript.py. Okay. So once these are complete, you have to recompile, because anytime you change the C++ layer, you need to recompile. But it seems that it takes more time to recompile, because one thing I want to highlight is that whenever you change the header file, then any library depend on this header file will be recompiled. In this case, I changed the DASolver.h, this header, and the recompiling this will take a bit longer. I got a questions. Yeah. Yeah, now the original version is finished. I think it's compiling the not the AD version. Yeah. Okay. Yeah, still compiling. Yeah, now you can see that it's compiling the AD version of the code. Let's wait for a while. It may take about 1 or 2 minutes. Yeah, it's almost there. Okay. So now you can see that recompiling this takes much longer because that you change the header file. A lot of the other libraries depend on this header file. It has to be recompiled. But now it's finished. Now, next thing is go to this directory. Nakadabo 12, cd, pastes, and then run this command as before. Now, what do we expect to see? We should be able to see that. Get a check. Let me check. So I get a question, why don't we need to clean the run directory each time? No, we don't, because the run directories, we are not running optimization. If we run optimization, yes, we do need to clean up the run directories. Right now, we just run analysis. We will not impact, yeah, we don't need to clean the run directory. Of course, you can clean it up and then rebuild the mesh and run it again. Yeah. Solving the flow won't create any conflict. You can solve the flow as many times as you want. Anyway, let's try to run it, see if it print out the mesh size. It should print it out at the end of the simulation. Okay, so you can see that hello world is there, my test option is there, the mesh size is here. Okay, and again, this is, as you probably remember, we didn't add it into C++ layer. Instead, this function is called on the Python layer. This function is called from the C++ layer. This function is called from the C++ layer. So alternatively, you can also call this new function recreate in the run script v4. If you open this run script, go to the bottom, find run model. So here's a run model, right? We can copy this line, copy. So you can also call it in the run script or any Python file, you can call it this function. So of course, remember to add the spaces. Yeah. Okay. So we first run the float, print out the mesh size, and also print the information, say print it in the run script. And then we use this format to actually print that function. It's a very long command, right? So just, it's hard to find this function. But anyway, then we run it again. You should see that mesh cells get printed twice. One in the pi DAFoam.py, the other is the run script.py. See, the first time is printed here. The second time is after the simulation is done, we can also print it in the run script.py. In the run script.py, you can call any functions you define in the Python layer. Okay, any questions so far for this part? Okay, then go to next. We have two more topics to go. So how to add a new object function or how to add the design variables, and probably we don't have time to cover the rest of the topic today. Now let's first check. This is I believe that this is a very common need. Like a new user may want to add a new object function and constraint function. Okay, so the DAFoam is designed to minimize the effort for this. And this process is very, very similar to version 3 with some very, very minor change. That's why I still want to go over this process, how to add a new object function. Okay. So first, go to the DAFoam folder. Go to DAFoam. Go to repos. Go to DAFoam. Should be in this folder, the DAFoam source code, the home directory, DAFoam repos, DAFoam. Okay. Then cd into this class called DA function. Cd in this function, right? And if you type ls, you should be able to see a list of functions that are supported in DAFoam. The very first one is the parent class called DAFunction. The rest of them are all child class. Each defines a different object function. For example, the force function, the location function, mass flow rates, mesh quality, moments, patch mean, many others. Okay, so let's create a new function called test function. And then let's use a DAFunction patch mean as the template, which means that what I'm going to do is that I'm going to copy this. Patch mean is here. And I will rename it as DAFunction test fun.c. Okay, now you should be able to see the new file right here. Where is it? Oh yeah, right here. So I create a copy of it. Now what I'm going to do is I view this file. Oh yeah, before that, we also need to do another copy, which is copy. We need to copy the header file, this one. To DAFunction test fun.h. We need to copy the .c file and the header file, both of them. Okay, so you should see that both of them are here. Then we can view this .c file. And so depending on how you want to edit this file, and you can copy it to a different place, you can edit it. But what I'm going to show you is how to edit in a VI command. So what I want to do next is that I want to replace this key with this, because this is my old function, this is my new function, right? So the way you can do this is colon percentage s slash the old key, copy, paste, slash the new key. This, copy and paste, slash G. G means that replace all. If you press enter, it will replace all these instances with this. Okay, so then remember to save it, colon WQ, save it. And do the same thing for the .h file. This is the h file. You can press colon up, colon W. Yeah. This is basically the same command. You can press colon and percentage and press arrow up from your keyboard. It will show you the command you used before, and just do it again. Or you can just type in again. Okay. Replace, and you can see that you replace all the instances. Okay. Just one thing I want to highlight, important. Remember to also replace the type name. This is the name you will need to use to identify this new function you created. So you need to replace this with the name you like. For example, test fun. Okay, and this name is case sensitive. Make sure that you use a small case or large case. Okay, once this is done, colon WQ, save this file. Now I create two new files and replace the class names, but this function is the same as my previous one, right? I don't know if it's working or not. That's why let's view this file again, this implementation. We will change this function slightly. Okay, pastes. We'll change this function very slightly. So you will do the same thing. You will just find a patch, calculate the mean variables for this patch. But at the end of the calculate function, so go up to find this calculate function. Okay. And then go to the bottom of this function, should be at line 107. You print some custom information to make sure that, or just you can say that this is my new test function. So of course, what you can do is modify these functions to actually compute object you are interested in. But here I just show you the overall process. The actual implementation really depends on users. So, but I want to print out some information to denote that, oh, this is my new test function, is not the old one. They make this change, save it. Okay. The modification is finished, but by default, DAFoam will not compile this new function because we need to add it into make file. Okay. So let's go back one level. There's a folder called make. You can view make. Inside this make is a file called files. View this file, you can see that this is the list of file DAFoam will compile. And your new test function is not in there. That's why you need to add it. DA function. Basically say DAFoam, please compile this file. I just add. It's called DA function. What's this name? Test file.c. So if you add this file in this here and save it, DAFoam will compile it, of course. And go back to the DAFoam folder and recompile it or make. So you can see that DAFoam managed to find this file, and if you scroll up, where is it? Yeah, he managed to find this file and then compile it. And this compilation will be very fast because you are not changing DASolver.h. Okay, let's go to the next. Yeah, it's ready to use. How do we use it? So let's go to this folder. Again, Nakadabo 12, paste. Okay, then we need to modify run script version 4. So we have a new function, we can use it. Let's scroll up to the DA options functions. Okay, scroll up. Yeah, right now we only define 2 functions, right? CD and CL. Now we can add a third. The third one is our newly defined function called my new test file. This is the name you will print out to the screen, and then you need to define the type. And this is the type name you just put in. This has to be test file. And then source, meaning that, of course, you can copy this block of code and paste in there, but I just wanted to tab. So I'm going to define the patches. So if it's just wing, you will calculate a mean variable name means pressure. So you will calculate the mean pressure on the wing surface. And variable type, this pressure type is a scalar, it's not a vector. Index, if it's a vector, you can prescribe an index. If it's a scalar, you can prescribe any index. And also you need to prescribe a scaling factor. I don't want to scale these variables, 1.0. And then that's it. Okay. So you can see that I define a new objective function. Now here's the place I can use it. Okay. And save this file and run it again. And how do we know that it is working? So if you look at a log file, you should tell that, oh, this is my test function. So it prints out a lot of things, right? So this is this basically verifies that, okay, yeah, it's calling my new function because it prints out a lot of things. Also, you get a new function called my test function. It computes the average pressure on the wing surface. Obviously, this is a related value minus 10. Okay, and this is it. If you want to add a new objective function or constraint function, and this is all you need to do. And the rest of the derivative computations, parallelization and stuff is automatically done in DAFoam. So you don't need to add any other things. So this, I believe that this really simplifies the process of adding a new objective function. Any questions for this part? Okay, then let's continue. Let's talk about the last topic we want to cover in this workshop, how to add a new design variables or input variable if it's more general. And before, in version 3, we need to add a few functions here and there. Now I'm going to show you that this process is simplified by a lot. Okay, we have about 10 minutes. I need to go a little bit quick. The very first thing is to go to the DAFoam folder, DAFoam, repos, DAFoam, and then cd into the source, adjoint, DA input. If you type ls, DA input is parent class. It has many child class that defines various input. It could be a field input, could be a FV source input, could be a patch variable input, could be a patch velocity input, could be anything. This input could be some boundary conditions, could be the viscosity if you want to define it. Here I'm going to show you how do you add a new design variables. We're going to follow a very similar process. We're going to copy one from the existing one. For example, I'm going to copy this patch velocity, DA input patch velocity, into this name, DA input patch Vx. So I just prescribed the velocity in the x direction. So do the same thing for the header file. DA input patch Vx.h. Okay, or you can copy paste from here. This process is very similar as the previous example. Then do the same thing. Open this new file and replace the input.c file. And we want to do this. Replace all these instances with this. Okay. So replace this with this. Let me move this out a little bit. Yeah. Okay, everything's replaced. Remember to save it. Do the same thing for the .h file. Colon percentage arrow up. You will go to the previous command, replace everything as well. Okay, you can see that everything is replaced with DA input patch Vx. Now let's scroll up. Type name is critical. So we can't call it patch velocity anymore. We have to change it to patch Vx. The type is called patch Vx. This is a new input type. Okay. Now, there's one more thing you need to change though. So in this header file, okay, if you look at this, in addition to add this type name, you also need to scroll down. The size. The size is important because every design variables, when you define them, you need to know the size. In the patch velocity, we know that it's a 2D vector, velocity magnitude and angle of attack. Here, Vx is just 1D, it's just one scalar. That's why the size is not 2, it's 1. Okay. The second parameter is distributed. Obviously, it's not distributed. Okay. You only have one Vx for the entire mesh. It doesn't matter how many CPU cores you use. But some variables, especially the field variable, you might be distributed across different processors. In this case, you have to set it to 1. Okay. The size and the distributed properties, you need to set it. And this is completely compatible with OpenMDL. So OpenMDL also need to provide a size. That's why we reformat the C++ layer to let it be more consistent with OpenMDL. Okay, that's all the changes you need for the header file. Now let's look at the .c file. Okay, so .c file, you hit enter. So there's a few places you need to change. If you look at the code here, the main function in this .c file is the run function. What it does is nothing but take this input scalar lists. It's a list of input. In this case, if size 1, it only has one element. all you need to do inside this function is to assign a value from this input key to the OpenFOAM's flow field. In this case, I will assume that this input key will have the Vx value OpenMV want me to assign. Then I will assign the value from input key to the OpenFOAM's field. In this case, the velocity field. Okay. So in order to do that, now I'm going to do a quick version of it. Okay. So before, so this patch velocity does a lot of things and then assign value to this. So in order to make it easier, I'm going to do a very code-specific modification to it. First, please follow me to delete these files because these are used for angle of attack computation, which is not needed because we just assign Vx. And then we do need to get a patch name. We want to know that you want to assign this Vx to which patch in your mesh. Once you get a patch name, you get a patch name here. Okay, you can delete this one. These are for debugging. We don't need this. And we don't need the flow axis. We don't need this. You can see that for the old one, you get a velocity magnitude from the first element of input. In this case, we replace this line with Vx is the first element from the input. Input is this one. Okay, we get a value. What we are going to do next is assign this Vx to the OpenFOAM's U field. Again, we don't need these. These just for angle of attack. This line we do need it. We want to get a velocity value from memory. This will be the OpenFOAM's variables. These lines we don't need. Okay, so you can see that we get a patch names, we get a Vx value, we get the velocity field. What's next is that we do a for loop to loop over all the patches. So it could be the in-outlet patch, could be the inlet patch, could be the outlet patch, whatever patch you prescribed. And then loop through this patch, and then loop through this mesh, and then assign a value. Okay. Before, because it's an angle of attack, we have to assign value depending on the flow axis. Here is very simple. All you need to do is change this to 0 Vx, and this one delete. So we just find the correct patch, and then we assign value to all the faces on this patch. And then we assign the value to the first element because this is x. If it's 1, it means Vy, but we don't want to assign Vy. So just assign Vx. Do the same thing for this. So just assign the first element of your velocity to Vx. Okay, that's it. That's the only change you need to do. So you can see that we changed the input type from velocity magnitude angle of attack to velocity in the x direction. Okay, depending on your need, you might need to modify this part. The overall goal is to assign a value from input list to the OpenFOAM's field. Could be a boundary field, could be any field. That, save the file. And then that's it. You just go back to compile. So the good news is that we completely restructured the DAFoam's code structures, and this is only thing you need to change whenever you have a new design variable. Oh yeah, we forget one thing. You can see that DAFoam doesn't compile my file. Why? Because we didn't add this to the make file. So you can add it to the DA inputs. So once you have this, you can run it. The rest of computations regarding partial f, partial x, partial r, partial x will be automatically handled in the DAFoam's new code structure. So you want to add a new design variables, just add a child class for the DA input class, and that's it. So we have 2 more minutes. Hopefully I can show you how to run this cd to this directory. Okay, view the run scripts, v for run script. So right now, we don't have it. All we have is patch velocity, right? So we can add a new input here called Vx in. So I have to type it. Vx in. The Vx in, the type is the type we just create. Patch Vx. The actual patches will be the inlets or in-outs. Actually, the components, well, components is the same as before. So just add this. Okay, so after you add this, it will add inputs to the solver component and function component. It will assign the velocity in x direction to the solver and the function. Of course, later you need to do something else. You need to add this part. Because you have a new inputs, you need to add it to the DVS, independent design variables components, and you need to connect this independent design variable VXIN to your scenario VXIN. This variable we just added through the input info. And then you can add this as the design variable. Say you can give an initial value of 10. After this, you should be able to run this script. Yeah. So basically, you will assign a new value to it. I don't have time for it today, but if you load the flow field in ParaView, you can see that it assigned the value 10 to the flow field. But of course, you can assign a different initial value. Instead of 10, you say my initial design variable for Vx is 20. Okay, then you assign 20. There's one caveat here that you may notice that I mentioned that in DA input info, you shouldn't define conflict input. For example, this patch velocity already assigned the velocity for the in-out patch. You also define another Vx. They will kind of override each other. So this is not the best way to do it. So if you really want to add the Vx in, you should delete these patch v variables. Okay. Okay, I guess that's it for today. The rest of the slides, I think you can follow the steps to do similar things, such as adding a new boundary conditions, adding a new turbulence model, and adding a new coupling variables, including adding a solver. Okay. All right, I guess that's it for today. Any questions before we sign off? Okay, if no more questions. Again, I want to thank you again for attending this workshop and your interest in using DAFoam. Let's keep in touch.